So welcome to the pre-recording of the first half of lecture 13, scheduled for the middle of the 5th week in this 8-week summer course on computer algorithms. We are going to spend 3 lectures on dynamic programming. This is the middle lecture, where we consider 2 applications or 2 illustrations. In the first half, we consider segmented least squares. In the second half, we deal with sequence alignment. Okay, least squares. So this is a slide coming from a linear algebra course. So we have some points, data points. So the motivation comes from data science or statistics. And we want to discover a trend in the data. So here you see that with least squares, if the y's are depending on the x, so the blue line kind of summarizes the red data points. So as x increases, so does y in general. So you see that sometimes the red points make a dip, but there is an upward trend. So we are replacing the data with a line, or more precisely with 2 coefficients a and b. A is the slope of the line, b is the intercept. And over all possible lines, we are doing this so that the sum of the squares of the errors, so we have the observed, the given y values, and then we have the value what our line tells us. So we are minimizing those distances. So this is an optimization problem. So also with dynamic programming, we are trying to solve optimization problems. Computing this line is something that you see in linear algebra. So, and the software that I was using for this example was least squares in Julia, with the least squares computed by the QR decomposition. Okay, so what is our segmented least squares? Well, suppose that we know that our trend is going piecewise linear, so we have an upward going trend, but then the trend, actually the slope, starts to increase. So here, if you look at the x-axis, we have the negative values for x. There is a very relatively small slope, but for the positive values of x, we do have a faster increasing function. So instead of replacing the data with one single line, we're going to generate 2 lines. So the way I constructed this example, I just picked 2 lines with slopes 1/2 and slope 2. So here you can read the numerical slopes 0.52, and the green line has a slope 1.96. So this gives us a much better data fit. You can think of an application where you want to reconstruct a piecewise trajectory, where you can imagine kind of a flight where the flight pattern changed a couple of times, and only the angle of the flight changed. Or you can think of a boat traveling on the sea. In any case, we do have data points that is following a piecewise linear pattern. And we have explicit formulas for this linear fit. So I said that this was a problem from linear algebra. You can actually derive those formulas, so that would be a linear algebra problem. But in this algorithms course, we are interested in the costs. And the problem is here for the first exercise, what is the cost of computing one least square line? And as you can guess, it is quadratic in the number of points. But you have to justify your formula. You can do this either by reasoning on the formulas and expressing the number of operations in function of n, or you could also write pseudocode, that's the alternative, and then observing the double loops with a constant number of operations in the innermost loop. Okay, so this is the first exercise. So here is the problem again. I took the same example as last time, and I changed the orientation now after 1. So we started with a small slope 0.5, then the slope became 2, and then after 1 the slope became very small again. Now the question is, can we actually detect this direction changes, and can we do this most importantly with an efficient algorithm, an algorithm that will run in polynomial time. So this is the input to our problem, data points. And of course, what we actually can't do, we can't really compute all possible lines through all possible selections of points. We have to be systematic in this, because all possible choices of points, that leads to an exponential cost. Okay, so here is the solution to this problem. You see again the data fits. Now the slope was around 0.5 of the last blue line, 0.2, sorry. Or actually, I cut, so the first slope was 1/2, second slope was double, 4 times 2, and then it was 1/4 for the blue line. So these are the exact numbers that I have used. So this is the solution of a constructed problem, or actually I worked backwards, first making the lines, then taking points with some noise on it, and then refitting. Okay, so let's formally define what our problem is. On input are distinct points. So here I'm consistently using X. It's also in many applications typical to work with time. So you have measurements. You can even think of temperature that linearly is changing at some point. So each point has an index, so has a number. So, and then we will define the segments as the beginning index and the end index. So a segment is stored as ij, where I is strictly less than j, and it contains all, well, we can have segments with 1 point, but in some sense, theoretically, that's possible, but we need 2 points for a line. So the segments will, although we can, if we have 1 point, we could exclude an outlier. So that's allowed here. We want to partition our data into segments. So a partition means that we have everything, so all points are included, and they are every point belongs to exactly one segment. So that's what a partition means. Here you see formally the first index of our first segment is 1. The last index of our segments, we have m segments. M is typically much less than n. The last index is n, so this means that we are excluding all of them. And then the next segment starts with the point immediately following the end of the previous segment. So this is what this formal definition says in words. So input points, output is a number of segments, where that number m is also part of the output. So we have the value m, and then we have m tuples, where every tuple gives the beginning and the end point of a segment. Okay, so then is the segmented least square problem formulated as an optimization problem. So we have the error that we still want to minimize. So the second part of this definition here is the sum of the squared distances. So this is what we want to minimize. Again, for every line in every segment, it needs to fit the data. Needs to be a best fit, minimize the sum of the squared distances. But we also have a penalty on the number of segments. In a very absurd case, we could take as segments all the consecutive pairs. And that would result in, say, a curve. Well, that's one of the algorithms to draw a curve. You connect you connect the dots. So that will give you a very high penalty. So the cost C is here left as an abstract cost, but if C is of course infinite, then you actually don't allow segments. That's also an absurd cost. If C is 0, then actually you can minimize the sum of the squared distances by just connecting the dots, taking as your lines the connections between 2 points, and there is no error on there. Okay, so C equals 0 gives you these connecting the dots. C equals infinity gives you the least squares, where you use one line. So choosing the value of C is something that is left here in this theoretical course abstract, but for the practitioner, you may want to run your algorithm with several values of C to see what you get. Okay, so then does this segmented least square problem have a unique solution? I actually already gave some extreme values. C infinity gives you the least square fit with one line segment. C equals 0 gives you another optimal solution essentially, but it depends on the value of C. So that's the solution of the exercise. Okay, so this is a lecture on dynamic programming. So we will apply dynamic programming, which we introduced in the previous lecture. So to be self-contained, what is dynamic programming again? It looks very similar to a greedy algorithm in which we locally optimized something and then proved that by optimizing locally, we obtain a global optimum. However, that technique doesn't always work. It's also very similar to divide and conquer, where we split things up and then we solve and then we recombine. Divide and conquer we applied to reduce quadratic to subquadratic, to cubic to subcubic, and we even had an example where you have a linear time that you reduce to a logarithmic time. Here, it's not that simple, because if you are dividing things up in subproblems, we must have a polynomial number of subproblems, and we should have a way to kind of eliminate many choices that cannot be optimal. There is also an easy transition in going from a subproblem to a larger problem and to the original problem. And in all cases, there is a recurrence that will be derived. So we emphasize a lot in this course on the mathematical formulations, what the algorithms, of course, central, but in the design of a solution, a dynamic program, we are going to start from a recurrence. In this lecture, in the previous lecture, we had choices either or. Choices were binary. Here we will develop multi-way choices recurrences. So in every step we have multiple choices to consider. Okay, let's go now back to our problem. So we will think backwards. So we will think about our last segment. Because we have a partition, the last segment must end with the last point. So, and now the question is, where does the last segment start? So, what is the beginning, I of m? Well, it will depend on the cost, so from the segment. So if the extreme choice again is when the I of m is n minus 1, but that will immediately get many segments. And then we also have the error of the fit. So if we pick again, if we have I of m, the start of the last segment, if that is 1, we actually choose everything. So you can kind of see what we'll have from the penalty. So we will have a cost from our segment, we have an error from the fit, and then we also have, and here you see now the recurrence coming in, it's the penalty of the partition of all the points that come before the start of our last interval. At the end, we will actually know what is the value of m, but for now it doesn't really matter. So we have I, that is our current index that we will compute. That's the start index of the last segment. Okay, so doing mathematics is often starts with definitions, but finding good notations is also critical, the way you write things down. So we will denote OPT as a function of I is the penalty for the partition of up to I. If you don't have anything, you have no penalty. Then we can state in the lemma here that the last segment in an optional partition has 3 portions in this penalty. And in some sense, this is formalizing in symbols, in a formula, what we wrote down on the previous slides. So we observed that the penalty of the last of considering all points It depends on the value of I. It depends on you have at least one segment. So you have that cost of each segment. You have the least square error. And there is a trade-off here. You can see already if the I becomes smaller, you only have one C in the limit when I equals 1, but your error will tend to grow. And then you have your OPT of I minus 1. So what does this lead to? Well, you have already here our first recurrence. So the penalty of partitioning the entire set is the sum of the cost of one segment, the last segment, is the error of the least square fit of that last segment, and it is the penalty of all the points that come before the last segment. So this lemma, which is derived, so in some sense, if you want a formal proof, you would go back to the previous slide. But in some sense, this lemma is summarizing the notation and deriving a recurrence. Now, here we have many choices. And what the lemma actually says, so if you want to read this fast, then you can choose all possible values for I. So if you pick in the extreme case I equals 1, then you have only one segment, but we have to consider this. It could be that there is only one segment. Or in the other extreme case, I equals n. And this could happen if that very last point was kind of an outlier. Well, you want to put it somehow outside. And the value of that outlier would still mean that by picking that last point, your least square fit of the segment that contains that point would shoot up too dramatically. So that's the rationale why, or the reason why I equals n is also a good choice. Okay, so and here you see always a little bit the aspects where dynamic programming seems to get close to the brute force technique. We actually consider all possible values for the beginning of the last segment. So we have the general recurrence. So this lemma here generalizes the recurrence from the previous lemma, which was considering only one particular value for the beginning of the last segment. Here we consider all possible ones, but we retain only the smallest one. So we will build a sequence of values, a sequence of optimal values. Okay, so here is then the recursive solution. So this suggests an algorithm, a recursive algorithm. Write this formula in pseudocode and draw the tree of subproblems. The solution to this exercise, for that you need to go back to the previous lecture where we introduced memoization. So dynamic programming resembles brute force, but you will need a lot of force if you don't work it out reasonably. The point again of this exercise is to show that dynamic programming works, because in the tree of subproblems you will see that you are solving the same problem many times. So the subproblems have a strong connection to each other. And that's also what we do with the memoization. Here, because we have already done the previous lecture, we've seen that from the memoization we can develop a direct iterative answer. And that is done here. So the M is that array that memoizes all the optimal values. So in each step, we have to compute all the errors, and you can see that the startup costs, I mean, there are initializations, so we initialize everything to 0. But actually, for all the pairs, we are computing all possible errors. So we consider the length of all the segments for all possible pairs. And while that might be, and we store this in a table, so we are actually computing the matrix of all errors, of all the line segments that we can make for all possible values for I and j. So this I subscript ij, you should see this as a matrix. And the cost for this entire table, so it will be quadratic if you think about this, but it will not more than cubic. So the maximum cost that you may have is where you have to compute first row and first column, where one of the indexes actually goes to n. And I think it's also, well, it's also only half of the table, but still. Okay, once you do that, then we compute progressively our table with optimal values. And we will take in each time, progressively we compute the minimum. And the last value in this M table is actually the optimal value, which gives you the smallest penalty, the penalty that comes from the number of segments and comes from the error, the least square error. Okay, so you can see that this J loop, we started thinking when we derived our recurrence backwards, but the J loop can run forward, starting from 1 to n, first point, last point. And when we evaluate M at J, we actually know, of course, we know what the penalty is for one segment, this big C. We have pre-computed all the errors of the least square fits, because essentially we did all possible of them, all of them, which seems again a brutal force, but it is polynomial in the input size. And then we have and the point I wanted to make is that the minimum actually runs for all I values from 1 to j. So we are going to consider the minimum of all the previously computed values of the partitioning of the I minus 1 segments. And we consider the cost of one extra segment and one least square error. Okay, this algorithm runs in polynomial time. First proof that this least square is correct. And this goes back to the previous lecture. How would you do this? You actually would need to have solved the exercise 3, where one observes that with memoization you get to a direct iterative solution. So the lemma, the fifth lemma, actually gave us a general recursion that expresses the penalty recursively. So the precise statement on the correctness is that the M, and we'll go back now one slide, the M actually returns OPT. So actually the output sentence, so segmented least squares returns the optimal value, the smallest penalty in the partition. So that is the precise statement. In the proof, you must follow the original recurrence and indicate that the original recurrence is transformed into a direct iterative algorithm. Okay, reporting these segments in an optimal solution. We went over that carefully. So you may want to know. So we went carefully over that also in the previous lecture on another example. So when we have the output of the previous algorithm, and the output is essentially one array M, we also have the errors there that we have computed. Then there is a recursive algorithm, but the recursion, so there is a base case. If the number of data points governs the recursion. If in the base case there's nothing to do. Otherwise, we find the index. We find the index I of the segment that leads to the end of the point. And that's the index that minimizes the cost, the error, and the optimal value of the I minus ones. So, what is the cost of this? I hope it's clear that this recursion, if you write down the tree, the tree of function calls, then you see that there is only one call that's happening to report segments at most. How many calls can you have? Well, in the extreme case, you can have as many segments as you have data points. This is highly unlikely, but that's already one bound. Then you must know that you have to find here a minimization. So you have to find over all possible I values, and that goes up to n minus 1. So there is another loop there that's happening. So in some sense, I have already indicated that the cost will be quadratic in n. You have to write down what I outlined. So the number of steps, the number of calls to report segments, and then also you have the minimization. That can also take a cost that is linear in n. Okay, I'm close to the end. So that algorithm, is it now efficient? So you have proven that it is correct. That's by following the memoization trail to the direct iterative solution. So if we compute the errors, then actually this requires n square steps. But actually every step, and that's where exercise 1 comes in, requires a linear number of steps. So this is why the first exercise was actually kind of critical. I may have misled you that the cost could be quadratic. But here we need the solution of this exercise. So you should go back and verify that the computation of an error is linear. So we have the initialization stage, the computation of the least squares, of all the errors from the least squares. that is actually dominating. That's cubic in the input dimension. Okay, so we have then that the loop, when we run segmented least squares, we have a loop that does n steps, and in every step we compute the minimum. So in the argument of the minimum, we have a constant number of operations, so 2 additions, and we also have the comparisons. Now, 3 elements summing up, but we're taking the minimum that can have j comparisons, where j runs from 1 to I minus 1. So we have the sum of all the consecutive values, all the natural numbers from 1 to n minus 1, and that is quadratic. Now the initialization cost dominates, or you could also say that the loop that we run in this algorithm, so the first loop is the initialization, the second loop is dominated by the initialization loop, the first loop. Okay, so this concludes this segmented least square problem. As another illustration of dynamic programming, now with the case where we do have not an either or, but we have multiple choices. So this seems to lead to a more potential explosion of the cost, but we still end up with a polynomial time algorithm, albeit a cubic one. Now the problem is very similar to linear algebra, in which the solving of linear systems, also even running one least squares, actually does this in cubic time. Okay, note that we compute the errors here without really doing a least square computation. That is also very interesting. Okay, so I will stop here. So the second part of this lecture will follow in the next pre-recording, where we see another application of dynamic programming. So this first application was more to statistics and data science. The second application is on matching similar words.